Welcome again to the NPTEL course on storage systems. In the previous class, we started looking at some problems relating to commit protocols, and we looked at two-phase commit and three-phase commit. Again, to refresh your memory, we had also tried to understand the difference between commit protocols versus consensus protocols. So we started looking at commit protocols. So I'll just briefly try to summarize two-phase and three-phase, especially as why they have the problems that we discussed. If you look at two-phase, we mentioned that it gets into a blocking situation. Okay. Why is it happening? We'll just quickly look at it one more time. So this, if you look at two-phase commit, you will see that up till this point, it's all preparation. All this while you're just preparing to do something. The only time when you actually do, when you really make some movement, is at this point. So when you get ready from all, you decide that okay, now I can actually make the move. That is, previously it was sort of uncertain, not clear what is going to happen, but now it's all clear, I am going to make a move. Okay. So this is the critical point in some sense. Okay. Now similarly, when you look at three-phase commit, you try to avoid that situation, and that's why you get into a pre-commit situation. In the two-phase commit, you actually do this flushing of your the coordinator flushes his state, and there's no way to go back. Here what he has done is he decides I cannot really do it right away because I might get into a blocking situation. So he says, okay, I'm going to see how the situation develops. How am I going to do it? I'm going to tell everybody what I'm going to do. Okay. Again, I'll look at it one more time in a slightly different way so that you can see the difference between the two situations. Okay. So as I mentioned before, in two-phase commit, you get a ready T from all, then you commit. Again, just let's understand what commit means. Again, as I mentioned, two-phase commit and three-phase commit are connected with those kinds of systems for which there is persistent state. Okay. These are distributed file systems or distributed databases or etc. Okay. So when each party has done something, they have some state that has to be flushed to disk. Okay. So this actually means what exactly are we meaning by this? We flush the transaction and commit the state, okay, and then only we send the message. As I mentioned before, you cannot send the message first followed by commit. Otherwise, then the coordinator code crash in between, and you already informed that you're doing it, but you are unable to flush it to disk, your state. That's why it always has to be flush the transaction, that is, you make it stable on the stable storage and commit the state. You made an irrevocable step you've taken. Then only you send the message, so the other parties know that you already done something. And other parties better follow what I'm doing. Okay. So the basic issue is that if you have committed, it cannot be unrolled, because if all the, let us say, buffers etc. have been taken back etc. etc. So there's no way to go back. You're committed. Okay. You can't be dilly-dallying too much. Okay. If you keep doing it, you get into at some point you have to actually make a transition. Okay. This is the place where it happens. Okay. So our problem is that having committed, before I send a message, I can also still crash. So because that happened, nobody really knows what the coordinator did. That's why I get to the blocking situation. I hope this part of it is clear. Okay. And basically the thing is, from your FLP result, remember the result which I mentioned about the Fisher, Lynch, Patterson result. What does it say? In a distributed system, consensus is not possible even with one faulty processor. That is the exact statement of the theorem. Okay. And basically this is what exactly, that's why the FLP result applies here. So you have to commit, then only you can send the message, but it's possible that after having committed yourself, nobody knows what you did. That's why you have the FLP result applying in this case. Now what is the situation with three-phase commit? Here I do not want to get into a situation here. So, what I want to do is I want to sort of tell myself, okay, I do not want to flush the transaction and commit a state to avoid a two-phase commit block. Okay, I want to avoid this somewhere. So, what am I going to do? I am instead inform others on what I plan to do. The coordinator is slightly wanting to not take any chances of getting blocked, so it is trying to inform others. So, now what happens is that if you take this particular stance, unfortunately get stuck into the two generals kind of problem. What is this problem? As I mentioned before, what is this particular problem? There are two generals and in between them there is a enemy, and both the generals have to coordinate to attack them at the same time, otherwise they will lose. Now, our problem is that any messages etc. that have to be sent have to go to enemy territory and the messages can be lost etc. Okay, and there is no solution to this problem. Okay. Now, you can see why that is the case, because now we can map the coordinator to one general and all rest of the guys to the second general. Okay. Now, because of this, you are not flushed your state and you are trying to make the two parties agree before the coordinator flushes his state. Okay. So, essentially you are stuck into this two generals problem now. Okay. There is no way to escape from this. Okay. So, the only escape we have is from an engineering point of view, we can say I optimistically try to solve the two generals problem till somehow I succeed. So, in a sense I am not live. Okay. I am correct, but I am not live. Here I am blocking, here also I am consistent, but I block. Here I, instead of blocking, I keep trying things. You might say I am blocked here, but I am here, could be in a live block situation. Okay. I keep on trying new things, things do not work out and I keep on trying. Okay. So, the way I can do it is by having a leader election to try new coordinators. I keep trying it till somehow I succeed. Okay. Of course, from this you can see there are two problems. One is that the leader election itself is a stumbling block, because if you look at it, what is the leader election all about? It is all about trying to figure out who is the leader. Again, it seems to be similar to our commit problem. Okay. Only thing is that you may have slightly lesser stringent conditions for this part. Okay. So, again you will notice one interesting thing about three-phase commit. Okay. As I mentioned earlier, when we were talking about the difference between atomic commit and consensus, we also mentioned the following: atomic commits attainable only on the assumption that the process failures are benign. Basically, because every party in the protocol, right, they have some state that has to be carried forward in case they commit. Okay. If you have any Byzantine failures, that means that you really can't do this atomic commit, just not possible. Okay. So, there are situations where when I am talking about things like leader election, right, here when I am taking a leader election, I do not really necessarily have some kind of state that has to be kept forward. I do not have to save it. For example, I do not have to flush those kind of state when I am doing leader election. So, one can argue that this is slightly simpler than atomic commit. Okay, because I do not have some state, persistent state that has to be made persistent as part of the protocol in case I agree on something. Okay. So, in a sense, you can see the atomic commit finally can devolve to a consensus protocol as a sub protocol inside it. Okay. And this kind of stuff is also important in other contexts. For example, if there is a storage system and I need to keep replicas, multiple replicas, and there are two types of, there are two messages I send, and I have to send it to two sets of replicas, and it is important for me that all the messages I send, the sets of messages I send, they are received in the same order in which I sent to each of the replica sites. Okay. So, here also there is some problem relating to how to make sure that all of them agree that all the messages have been received and in the same order it was sent out. Okay. So, these things do not have a persistent state as part of the problem to be solved. Okay. In case it does not happen, you can again restart again, you can retry one more time, it is not a problem. Okay. So, it turns out consensus problem has a slightly simpler aspect to it. If things fail, you can retry. Okay. Whereas in the case of atomic commit kind of situations, you really have to flush the state that has been accumulated as part of your whatever transaction you are doing. So, it is a slightly different problem. So, what we will do is now we will start looking at, instead of looking at the kind of commit protocols for which persistent state is so important, we will try to look at closer to consensus kind of problems. And one important such solution is called Paxos. So, we will try to look at this particular problem, and this was solved by a famous computer scientist by the name Lamport, Leslie Lamport. It was also solved by other parties previous to this, but he had a very colorful way of talking about it. So, I think the word Paxos etc. have stuck. Okay. But 2 or 3 other researchers also have come with similar solutions before. So, let us look at what this particular algorithm is about. You have clients, proposers, acceptors and learners. Clients are those which are waiting for some, for example, some resource which is shared by multiple parties. For example, somebody wants a write lock in a distributed file system. Since it is a write lock, only one party should be allowed to be given this permission. Okay. So, clients are those who request this kind of requests. Okay. And we do not care who actually gets the request, as long as only one person gets. Again, this example of mutual exclusion. Okay. And so, clients make requests for mutual exclusion and they wait for a response. Okay. Then you have a set of proposers who attempt to figure out who should be given access to the lock, for example. So, that the party who should get it is the value. For example, if 5 people are waiting for it, you can say number 5 or number 2. Okay. So, proposers are basically the parties. There will be a few of these proposers. Essentially, the reason why you have multiple proposers is that in case there is a failure of proposer, the other proposers who know that this particular request has been made. Okay. You have proposers so that you remember that a request has been made, even if some of the proposers die. Okay. And they try to figure out what value should be decided upon. So, there are 5 people waiting to get a write lock. You should say one of them gets it. We do not care who, okay, but one of them should get it. And by collecting acceptances from majority of acceptors. Okay. So, proposers are saying what value should be proposed, and there will be a majority of, there will be acceptors who will essentially says, okay, it is fine to go with 4, 5, whatever. Okay. And then once it has been accepted, it is possible that there are other failures in the system and you can't remember what really happened, and that is basically ratified by learners. And the learners are basically the party who are some kind of replicate information somehow, so that the clients can get back the information. Okay. So, it is a very general model. Oftentimes many of these things are co-located, but for the purposes of this thing, we can assume there are various types of entities in the system. Clients make requests, proposers sort of remember what kind of requests have been made, so that even if there is only a single proposer, it might, if it dies, it is a problem. So, that is why there are multiple proposers. Acceptors are the parties who actually have some state, and they will try to remember what happened in the past also. Proposers will not have any state, persistent state, but acceptors will have. So, in case some thing has been decided in the past, they can look up the state and say, yes, this particular thing was asked, some bad stuff happened, but I still know what happened in the past. I can provide that. That's why these guys have state, persistent state. And those are the parties who actually can, there is some kind of a replication of that information about what was actually agreed upon. Okay. So, only one proposal can get votes of majority of acceptors. Okay. So, essentially there is some kind of quorum here. Here I am talking about majority, but it can be some type of quorum. Okay. So, our problem is that if you look at it, what is the problem in the previous case? What you were trying to do was to do a leader election. Suppose you say the leader election is a stumbling block. So, instead of doing leader election, I basically say let anybody start it, does not matter who. Okay. I do not try to go through a leader election algorithm per se. I will say anybody who sees that something is stuck, he can proceed. He is not going to do a leader election. Okay. That's a basic thing that Paxos does. Okay. So, essentially what you have to do is, when there are more than multiple parties who suddenly say that, okay, I see some problem, let me start a new round of saying that let the value be this particular, I am going to restart the protocol so that a new value can be decided. Okay. So, if there are multiple proposals, it turns out that you can wait for each other, and therefore, there can be some situations similar to deadlock that arising. So, to break those things, proposals can effectively restart a protocol by, if you see that the previous attempts to negotiate a value were not making headway, then you can just drop them and restart it. Okay. And if in the past some acceptors had decided on some values, okay, and those values cannot get a majority, if it is very clear that those values will not get a majority, then you can ask the acceptors to flush their state and to start a new round and then try to see if they can come to a new consensus again. Okay. So, this is a high level idea about what is being done. Essentially, it is slightly different from Paxos, slightly different from 3-phase commit protocols in multiple ways. One is that commit protocols, there is an issue about state that has to be flushed, persistent state, okay, which is critical as part of the let us say as part of the protocol. Here we need to have persistent state only to decide upon the value, but we do not care about what value we actually pick up. In case something does not work out, I am willing to go with a new value, it does not matter. Whereas in the commit protocols, I can't do that. Okay. For example, if a hotel has been booked and we are trying to proceed, that what hotel I booked is important, I cannot just let that drop it, okay, unless there is no agreement at all, then we have to drop it. Okay. If somebody is trying to move forward and they have already said that this particular hotel is important, you cannot drop it. Okay. So, there is some difference in the two types of problems. So, here what we are doing is, we can have, without going through leader election, we try to restart the protocol again, and one way to do it is by making sure that if any intermediate, if in the past some people have decided on some particular values, if you can show that those values cannot be accepted by a majority, then it is easy to drop them. Okay. That is basically the idea. So, again I am going to do it in slightly in 2 or 3 attempts to make sure this is very clear. So, I will first let us take a high level idea. Okay. So, before taking a vote, a proposer checks by sending a prepare n message to all acceptors. N is a proposal number. Okay. In a sense, one can say it is like let process phi get the lock. Okay. Let node number get particular lock number something. Okay. That is basically the proposal. Okay. Okay. So, that is a proposal. So, basically there are various proposals in the system, it will be monotonically increasing, let us say. An acceptor responds to the promise never to accept any proposal with a number less than n. Okay. So, basically the idea is that older proposals do not get suddenly ratified. Okay. There are some dormant or dead protocols, dead proposals which should not be accepted. So, basically some guy is proposing some n, and there are various acceptors who will, if they accept this particular n, they will basically say that I am going to, whatever I have done in the past, okay, I will make sure that I do not accept anything less than n. Okay. Okay. That is, I will, if somehow, because the reason why I have this problem is that there could be multiple proposers doing at the same time. Okay. So, they might be sending something else also. So, their number might be less than n. So, in which case I am going to promise saying that I will not accept those. Okay. And then in addition, since he has got persistent storage, in case in the past he has accepted a proposal, okay, he will send the highest number proposal that the acceptor has accepted. Okay. So, the proposer can substitute this value for its own in case previous value was in fact ratified. So, our problem is that some new guy has come in, he is trying to propose some value, but it turned out that in some previous situation a value actually was proposed and it was accepted by a majority, but before it could be let us say communicated to everybody, the proposer himself died. Okay, so so thing is that in some sense a majority was found, but the presiding officer died or something of that kind. Okay. So, now if that is the case, a new presiding officer comes in, he sees that he is able to figure out by talking to most of the people that in fact some particular thing was already accepted. So, if the acceptor sends back what proposal number that was accepted in the past, then the proposer can see if the majority actually got it, in which case he can say, okay, instead of proposing a new value, I will take whatever was accepted in the past. Okay. Again, we will go through it one more time to make sure this is clear. Okay. So, if the proposer receives a response from majority of the acceptors, the proposer then does a second phase of voting which sends it, where it sends an accept n comma v to all acceptors and wins if it receives a majority of votes. Okay. Again, let us go through it one more time. What exactly are we doing? First of all, we have a proposer who sends a prepare n message. As I mentioned, the important thing is, if you look at 3-phase commit, you are basically, the way you are trying to make progress there is to solve a lead election problem. Okay. But this itself seems to be as difficult as a consensus problem itself. Okay. It does not seem to be any simpler. So, the idea is to, instead of devolving to lead election, you try to do, you let people propose without worrying too much about if other proposals are there. In the case of 3-phase commit, you do not do that because there is state that has to be saved. Okay. So, it is a slightly different problem. That is why it makes sense in 3-phase commit to try to go through lead election. Okay. Okay. So, a proposer, he sends a prepare n message to all acceptors, and then acceptor, he either responds with a promise never to accept any proposal with a number less than n. That is, he is basically saying that I was involved in some things in the past, things did not work out. So, now that you have come along and said I have a new proposal, since nothing in the past, whatever I know about has not worked, I am going to accept yours. But I am also going to say that it is true that I have not heard from anybody whether the previous proposal got accepted or not. Okay. I did accept, but I do not know whether there was any majority, I could not figure it out. So, but I accepted. So, I am going to tell you what I accepted, what number I accepted. Why is this going on? It is because it is possible that he has accepted an older value, but he never heard about the fact that it was accepted. The majority actually was there, but somehow all kinds of failures happened, multiple failures happened, he never heard about it. Okay. So, that is why he is taking a stance that a new thing has come to me, I am going to accept it, but at the same time I am going to tell you that I was involved in some previous round where I accepted this thing, but I do not know what really happened to it. So now the proposer here, he receives a response from majority of the acceptors. Then the proposer does a second phase of voting where it sends accept n comma b, okay, to all acceptors and wins if it is null. Basically what happens is that if all the guys in the majority, they all say that we were all part of an old round, we all accepted this guy, just that somehow we never heard what happened after that. So this proposer hears from everybody saying that there was a majority in fact for an older proposal, then this proposer has to take that value and send it back, send it out. If in case there was no majority, then he is free to propose a new value b. Is this clear? So these are roughly the idea. So we will, so what are the safety properties that Paxos guarantees? First is, it is non-trivial. What does it mean? It means that only proposed values can be learned. Okay. It is trivial in case if everybody says always 0 or 1. Okay. It is a trivial thing. So it is not one of those things. Okay. Consistency. At most one value can be learned. That is, two different learners cannot learn different values. Very critical. This is a absolutely critical thing for distributed file systems and distributed databases and other kinds of systems which require mutual exclusion sometimes, okay, or often. Okay. So consistency is very important. Liveness. Value C has been proposed, then eventually learner L will some value. Okay. So if sufficient processors remain non-faulty, again there you can see that there is an eventual thing out here. Again that is why it is not live. It is not a liveness is not guaranteed here. Okay. So essentially, if what we are talking about right now is that eventually there will be some value that will be finally accepted if sufficient process remain non-faulty. Okay. That is when. So again, we are going back to saying that we can't really guarantee liveness, but it will, if you wait long enough, it will happen. That is basically what we are saying. So again, I will go through in some more detail to see exactly what is going on. There are various versions of Paxos, and we are going to now talk about the basic version. Okay. For efficiency's sake, we can do a lot more additional things, but we will look at the basic one. Okay. So every time we run this basic Paxos, we can say that each instance of this basic Paxos decides a single output value. Again, this is like a consensus. Basically, we are solving consensus. Okay. So here we have a quorum of acceptors. Okay. So proposer, there are multiple proposers, and there has to be a quorum of acceptors. Okay. Typically, quorum can be majority. And why is this important? If you have a majority, that means that it is always the case that two majorities will always have somebody in common. If you take two majorities, there has to be somebody in common. Okay. That is how information leaks from one round to the other round. Okay. Without this particular aspect, you really do not have any guarantees. So if you have a quorum, then the basic idea is that in case something was committed in the previous rounds, then two quorums will have a common party. Since there is a common party, when a new proposer comes along, then that information is going to go back to the new proposer, that in fact something was committed in the past. Okay. Okay. So basically, this has got two phases, phase 1 and phase 2. Again, these are somewhat similar to what we saw in two-phase commit or three-phase commit. I think it's looking closer to its elaboration of the three-phase commit, three-phase kind of model. In phase 1, there is a proposer P. We can also often call it leaders. Leader sends a prepare message, proposer N. Okay. And important that the P should know that he can't be sending any message which has the same number as previously has sent. It has to be greater than any previous one sent by P himself. to Q. Basically, he is sending it to quorum of acceptors. So, there are a bunch of people who are there, he is going to send it to them. Okay. Now, once it has gone there to the quorum acceptors, now it is a turn of the quorum acceptors to promise something. What are they promising? If the number n that has been received in this round is greater than any previous proposal received from any proposer by an acceptor, okay, then acceptor must return a promise to ignore all future proposals less than n. Okay. Again, we discussed it before. It's basically that there are concurrent proposers now. Okay. So, what it means is that this particular acceptor was involved in some things in the past, and he is going to now promise that he is not going to accept. If he accepts this particular promise, that means he is not going to, he is going to ignore all other future proposals that could come, because they could be delayed. Okay. See, there could be, the assumption here is extremely general. Your messages can be duplicated, it can be delayed, it can be arbitrarily delayed, okay, dropped, all kinds of things. So, some previous proposal could come to me now, okay, and that number could be smaller than the one which I have. Okay. Okay. So, the acceptor must return a promise to ignore all future proposals. Again, you can notice this is similar to in 3-phase commit. The pre-commit phase is basically some kind of a promise. It is basically promising to everybody else that I am ready to go forward, I want to flush, but I am going to inform to all of you guys that I have agreed, but until I hear from you, I will not flush. Okay. That is basically the promise. Something similar is going on here. Okay. If an acceptor accepted a proposal previously, it must include previous proposal number and its value in its response. Okay. So, now what has happened is that, again as we discussed before, if this acceptor actually was part of a previous round and he had actually said I am going to accept it, but he somehow has not heard about how it progressed in the past, he has just not heard anything after that. Okay. Then it is possible that by sheer let us say set of circumstances, actually that particular previous thing round actually succeeded and they agreed upon it. It's just that I never heard of it again. Okay. That is the reason why it has to include previous proposal number and its value in response. Okay. Otherwise, the acceptor can ignore the received proposal, can just drop it on the floor, it does not have to do anything. Okay. So, this is the second part. Then the third would be accept request. Okay. If P receives, that the proposer receives enough promises from Q, it needs to set a value to its proposal. Okay. The question is what value? Okay. So, there is enough quorum now. Okay. There is a quorum. So, it needs to set a value to its proposal. If any acceptors in Q had previously accepted any proposals, P must set value to that of the highest proposal number reported by Q. Okay. If none in Q had accepted any, then P may choose any value. Okay. This one is easy. If none in Q had accepted any, then P may choose any value. That is perfectly fine, because there is nobody has accepted anything, therefore it is okay. Okay. So, if any acceptors in Q had previously accepted any proposals, P must set value. Basically, it turned out that there was a quorum actually for some previous value, then it is duty bound to put that value. Okay. In that case, it either puts that value or the one which it selected because there was nobody, there was no quorum for any previous values, it sends an accept request to Q with value. Okay. In 2B, basically now the proposer has actually sent accept request n with the value, then all the acceptors, if they receive a accept request, okay, must accept it if it has not already promised to only consider proposal greater than n. Okay. So, notice that it must accept it if and only it has not already promised to only consider proposals greater than n. Okay. So, again it is an interlocking aspect like what we saw in phase 2, phase 1B. Okay. So, So, if it accepts, then you have to send the value v with an accept message to p and every learner, else you can again drop the request, completely just ignore it. Okay. So, this is roughly the Paxos algorithm. Basically, the rounds fail when multiple proposals are there and they send conflicting prepare messages, okay, and they get interspersed each of these requests, and each party can decide that okay, I don't want to be part of this round. So then the rounds fail for that reason, because there are not enough people to agree on a particular value. Okay. Okay. So you basically have to restart the round with a higher proposal number. Okay. What is interesting about this is that this particular protocol, it will survive any failures from anywhere, okay, whether it is proposers, acceptors, okay, it does not matter who fails, how they fail, it does not matter at all, okay, it can actually survive those things, okay, because it guarantees that it is, if a particular value has been decided upon, okay, by majority of people, that will be picked up again, okay. So, there is a consistency condition is guaranteed, and it is very critical, because if you are talking about locking situations or mutual exclusion situations, the consistency aspect is very critical, otherwise we can have inconsistent system. But the basic problem here is that once you have this kind of system, you no longer guarantee liveness, okay? That is basically the issue, okay. I have taken some diagrams from Wikipedia where it gives the same diagrammatic. So, we will look at quickly some of these cases. This is a client which wants a particular service. Actually, I should mention that if you look at Google, there is something called a chubby service. This basically the clients, these are guys are making what is the equivalent of chubby calls. Okay, these are basically making a request saying that give me a particular lock. Okay, give me a particular value that all of us will agree upon. Okay? That is what this is. Okay. So, proposers, there is one proposer who hears this request, there could be multiple of these guys, okay. This particular hears it and it tells the acceptors, right, I am going to propose a value 1, do you guys all agree, okay. So, it is basically saying prepare 1, and all these parties now say promise 1, and they have not seen anything in the past, they have not been a part of any round, or some rounds have happened so far back in time that everything has become quiescent, okay. So, we will say null in that case, okay, there is nothing there, okay. So, they are basically saying that I promise that I will, let us say, I am basically saying that I am willing to go ahead with what you are proposing, okay, and I do not have any previous things that have all been part of, okay. And once all these messages go back, the proposer in turn says, okay, now that I got all the right responses from all 3 of you guys, okay, I will send an accept saying that it has proposal number 1 with a value which I decided. Again, here the proposer is deciding value v, okay, not any of these guys, because they all sent null, okay. And then once I get that, again the acceptors now essentially handshake back saying that we accept what you proposed, okay. Here is a basically command to say accept, is basically here saying yes, we accept, that is basically what it is, okay. And the learners basically keep track of the information, so that in case it request, it can be responded to back to the client later, okay. This is roughly the outline of the sequence in case the first round itself is successful, okay. It is a very obvious case, but what we really have to worry is what happens if the proposer does something and dies somewhere here, or some acceptors die somewhere, or the learners die, etc. We have to figure out what all happens here. I am not going to go through all the cases, I am just going to go through a few of them. So, let us look at a case where there is a failure acceptor. So, it is also a simple case, but we say quorum size is 2 acceptors. Similarly, here also client makes a request, and then proposer proposes a number 1 as the proposal number, sends it to all the acceptors, and it turns out that one of the acceptors dies, but there is a quorum still. Because there is a quorum and both these parties basically say that I was not involved in any previous round, I have value null, right. I am willing to go with your proposal number 1, okay, that is what this is. And the proposer finally sends back saying, I decided a value v for you, take it, that is what this is. And here basically what is happening is that the acceptors now, having got the value v, they are basically saying back, they are saying that yes, I saw your value v, I am going to take v as the value and I am acknowledging it, okay. And the learners are there to be able to relay the information back to client, so that in spite of whatever happens here, one of these guys, there is some additional levels of redundancy or replication here, okay, which essentially tells the information back to the client. This again is a simple case. What about the failure after doing something he dies? Okay. Again the same story, client makes a request, X says prepare 1, and then all the parties here, they all say, they promise saying that yes, I heard you, they were not part of any other previous round, so we will go with your proposal, the proposal number 1, okay. So they send it back, but while he is trying to send thing back, he dies, okay. So basically what happens is that these parties do not get this value, whatever was accepted, okay. Okay. So what he was initiating, he was trying to say accept 1 VA, but somehow it did not get through, okay. So because this particular proposer died, okay, you can have some other proposer come in the picture who has seen that somehow there is something not okay in the system, okay. We do not care when it comes up, how it comes up, it can be any time, okay. He decides to say that I have a new proposal, prepare 2, and this is similar to what happened in the previous case, okay. So here I have listed this Wikipedia article talks about as a re-election, but it can be actually concurrent, okay. This actually can be somewhere concurrent, because this guy can decide to arbitrarily decide something is not working somewhere, okay, and decide, okay. So we will come to that kind of situation where there are multiple proposers operating at the same time. You can also have slightly more complicated situations. This one is slightly more involved. Here what happens is that just like previously, this client makes a proposal, he says prepare 1, and all these parties are basically saying yes, I am ready to go with you, but this leader fails, a new guy comes in, he starts the new protocol again saying prepare 2, and he sends all the second part, because all these guys have not heard about what happened to the proposal number 1. When they say new proposal, they decide okay, we will go with this new guy, okay. That is what they are doing here, promise to null, 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 because they did not accept anything so far, okay. Okay. They just promised, that is all, okay. So they send back this particular promise. Now the old leader can recover and he can try 2, okay, because he knew about 1, so he is going to try 2, but if he says prepare for 2, then all these acceptors, they can send an saying that we are no longer comfortable with what you are proposing, okay. So that is what this is, that no acknowledgement, and then the old leader tries, sorry, what did you do? So now the old leader tries 3, so prepare 3 is sent out. Now again these parties, these acceptors have not seen any progress with respect to 2 also for some reason. So they will now say okay, I saw a 3, but now I will no longer accept anything connected to 2 because that was not going anywhere. So, it now says I am promising to see if 3 can be made to go forward. That is what this is. And now the new leader that came in, now he says accept. But if he says accept, because these guys have already said that they are trying to see how the proposal number 3 is going to fare, right? They cannot accept what the new leader has proposed after the first leader died. Okay. So, that is why there is a knack again here, and the new leader tries 4 and he says prepare 4. For some reason again prepare 3 was not going anywhere. They will probably decide to go with round 3. Okay. So, you can actually have a situation where multiple proposers keep on overtaking each other, and it might not really converge. That is possible. Okay. But important thing is that the minute there is any convergence and majority of the guys agree on a value, because of the quorum kind of property, even if one party agrees on, right, the other, any new quorum that starts, they will know about that particular value. It is the same principle that is formed in committees. If you look at a government system, you will find a lot of committees. Invariably, there is always one or two parties are always common to certain multiple committees. And because of that, what happens is that any decisions taken in one committee is always known to the other committees also. Okay, this is a part of the way most governmental systems work. So, let us just again summarize Paxos. It is run by a set of proposers. They are highly non-deterministic. They can start anytime they like and without persistent storage. Okay. That guide a set of acceptors. These parties are deterministic with persistent storage that survives crashes, because they have to remember what they were doing sometime in the past. If, for example, they were part of a particular proposal and they had agreed to commit a particular value, right, to agree on a particular value, they have to remember what they were doing. So, that is why they need persistent storage. What is interesting about this is it's correct no matter how many simultaneous proposals there are, and no matter how often proposers or acceptors fail and recover, how slow they are, or how many messages are lost, delayed or duplicated. Okay. It's a very interesting property. It's non-trivial. Okay. What is important also is that it terminates this particular protocol if there is a single proposer for a long enough time during which the leader can talk to a majority of proposers twice. Again, you can see why it is twice, because if you look at the phases, phase 1 and phase 2, you need at least twice. Again, if you remember the timed asynchronous model we briefly mentioned, there also the model is that it is mostly stable and once in a while unstable. Okay. So, the thing is, if it is stable enough, then you can get something, you can get forward progress. Again, something similar is going on here also. May not terminate if there are always too many proposers. Okay. Guaranteed termination is anyway not possible. Okay, so it turns out you can do something slightly better. If you want looking for liveness, you can combine Paxos with a what is called a sloppy timeout based algorithm for choosing a single leader. Okay. So, basically the basic idea is that if you are able to choose a single leader, then that particular person's value can be made to stick. Okay. That is basic idea. Okay. The sloppy algorithm leaves us with no leader for more than one leader at a time, because of partitions etc., it is possible that there can be more than one leader. Okay. So, for that reason it may not terminate, but if the sloppy algorithm ever produces a single leader for long enough, the algorithm will terminate no matter how messy things were there. Okay. For example, an example of a sloppy algorithm for choosing a single leader is following. Suppose the proposers have clocks, max time to send, receive and process messages no. Okay. Suppose you know these values, then every potential leader that is a broadcast its name. Okay. Now, a proposer becomes a leader one round trip of after doing a broadcast, unless it has received a broadcast of bigger name. Basically, what it's doing is everybody broadcasts, and then because it knows about the max time to send, receive and process messages no. Okay. It decides after one round trip that it is a leader. So, mostly if things are reasonable in the system, only one guy will win, because everybody is following this protocol that if it has received a broadcast of bigger name, it says I cannot be the leader. Okay. So the biggest guy wins. Okay. But if it so happens that there is some network problems and whatnot, or the system is very unstable, then multiple parties can believe that because I have some kind of max timeout, right? I have some max amount of time here. I can decide that, okay, I have not heard anything bigger than my name, therefore I become a leader. But it turns out that multiple parties can come to that conclusion, and so therefore again you have a situation with multiple proposers, and they have to duel it out. Okay. But if the system is reasonably stable, then only one of them will essentially win, and you can proceed. So in a sense, you can slightly make it easier, instead of the completely open situation with the Paxos where anybody can propose anytime. If you use this floppy method, you can essentially try, if the system is reasonably in a sensible state, okay, without too many failures, it will actually be very, very quickly. Okay. So these kind of algorithms are used in many large scale storage systems, and as I mentioned, Google has in their for their various clients, they have a locking service which I am told uses Paxos within it. Okay. So and various other large scale storage systems or web scale systems also use Paxos kind of models, and so I think I will conclude here today, and I will continue with a similar set of problems, but more close to what is called group communication systems, where you have to order the messages. And this again is quite critical for storage systems, because they might want to keep some metadata which is consistent amongst multiple nodes, and they have to exchange messages to come to that consensus. And if it turns out that if messages sent out go in different orders for two different sets of messages I send, then there could be some confusion about what really happened on the receiving side. So there is an important aspect in large scale storage systems to figure out how to do reliable message delivery, so that multiple messages I send, they go in the same order, or similar types of constraint receptions have to be guaranteed on the receiving side. And we will look at that one, and we will again connect that particular problem to the kind of problems we saw before, either commit or consensus kind of problems.